Hello, just thought I'd show you a little something I've been working on. I'm holding in the palm of my hand, almost, an entire LinuxCNC build minus, I guess, the ball screws and the linear rails and the actual spindle and that stuff, but all of the computer control part of it here I'm just holding in the palm of my hand, and I have some RGB LEDs showing me what's going on and a little set of colored buttons there. So what we have here is a computer running LinuxCNC. That's the Raspberry Pi 0W there, and that is connected by SPI connection to this programmable real-time unit, which I designed and mostly wrote the source code for, although it was heavily based on something called Remora, which is maybe familiar to you LinuxCNC users, and that lets you do quite a few things actually, but the code that's running on this particular unit is probably about 90% my code at the moment, and that's running on this STM32 microcontroller there, which is basically the micro that you have on a blue pill. So you can actually run this on a blue pill, although the connections get pretty horrible, so that's why I designed this board to make it a little bit tidier. So also on this board we have some stepper driver carriers where you would plug in your stepper drivers there, and a bunch of pins, and there's a level shifter there which didn't really work out, at least not yet, and some inputs and some optocouplers over there, which I haven't tested those yet, so probably should have tested those before making this video, but anyway. And then down here we have a rotary encoder, which I'm using at the moment to alter the feed rate. I have 3 buttons on this little panel here. Green is to start cycle and red is to abort or stop, e-stop I guess. The one in the middle will set the current position to 0. Let me just put this down, my hand's getting a bit tired. Ugh. And that will also let me push these buttons. So there's my green button there. There we go. So the program that it's running is the typical LinuxCNC text program that you see when you open up the Axis. It's like the default thing that shows up at the beginning, and it's running it as fast as those little motors can go. Those are NEMA 11, I think, motors. This one here is not going to be moving because that's the A motor, doesn't have any part in the program that's running. And the step rate that we're getting out of this is 50 kilohertz, which I think is pretty good. I'm not sure you could go a whole lot faster with that pretty basic microcontroller. But as I said, or did I say? I can't remember. Got a rotary encoder here, and I'll just turn this a bit that way, and I'm using that to change the feed rate. So you'll notice it's going a bit slower now if I turn it way down. Turn it way down like that, so we can alter the feed rate on the fly. And this rotary encoder could be used to jog an axis instead, like a manual pulse generator. It's just that what I've set it up to do at the moment is to change the feed rate. There's a few other inputs here for analog and stuff, but I think I'll show you that at the desk later on in a little bit more detail. Oh, and these lights here signify which mode it's in. So the one on the left just means that it's connected to the LinuxCNC side properly, and that's what that little green LED on the board there is showing as well. It just means that the SPI connection between the Raspberry Pi and this PRU is working properly. The second light there, which is blue, supposed to be blue, doesn't really look very blue here, but that just means that it's in auto mode because it's running a program. So we have green for manual and red for MDI, and then the yellow one there means that the spindle is on. Well, we don't have a spindle, but it would be on if there was one. Anyway, so that's all running quite happily there. Some of the other pins we have on here are just a breakout for the step and direction pins for each axis. It only supports 4-axis at the moment, and probably just leave it at 4-axis. But over here we have another setup of basically the same thing, except that this time we have a Raspberry Pi 3, I think if you were setting up a serious installation, you'd probably want a Raspberry Pi 4, but I don't have one, so I've just been testing with this. But I'm already starting to think maybe I could upgrade my big router out in the garage to use this, because it might actually be a little bit more convenient in some ways. But anyway, those step and direction pins that I was just talking about there, this black and white, whoops, that strip there, and as you can see down the end there, I just have one set of step and direction coming out, this set of blue wires here, and that's going into this rather nice closed loop stepper driver that I got from Stepper Online. They have some really good prices there. If you're looking for stepper motors and drivers, you might want to have a look there, because I was quite surprised at how reasonable the prices were. And the motor for that is this NEMA 23, which I bought for no particular reason other than that it was reasonably priced, which is a bit dumb, but maybe I'll use it for something in the future. And I don't have a nice button on here to start cycle for this, but just to demonstrate how this real-time unit could be used with like these larger, more serious stepper drivers, I can just touch, so not running there, but if I just touch that one, can I just touch there please? There we go. Alright. So this is just the x-axis running the same program. Anyway, I think you get the idea. This is also running off battery. So I've got 12 volts running the this stuff here, and the Raspberry Pi. So the Raspberry Pi is powered through this, of course. You don't have to do that. I set it up so that there is a solder bridge there so that we can back power the Raspberry Pi if we want to, which is what I'm doing at the moment, but you might not want to. You might want to just power the Raspberry Pi off the USB there, which is a little bit more typical way to power it. And I've set this to be running quite fast too, so that program's already finished. Yeah, so this is running the Raspberry Pi and the PRU, and the power for the stepper driver is coming from this 36 volt battery there. Okay, let's have a bit closer look at this board. It looks like there's a lot going on, but if you take a look at how the board arrived to me, I got these from JLC PCB. It's actually not that much on it. It's only when you put all these pin headers on that it looks so busy. So let's start from the left hand side. This is Raspberry Pi pin header. We don't need all of those pins. We mainly just need these ones for the SPI, and also the back power 5 volt ones. There's nothing on the back, by the way, but these pins here, these two there are 5 volts, so that's where the back power comes from. So we do need those, and then we need the SPI. We don't really need this one here. It's just for, you know, physical support. And also I think there's a couple more grounds in here. I've found that it really helps to have good ground connection between the Raspberry Pi and this board. Had a lot of trouble with that in the early days while I was trying to figure things out. Yeah, so that's SPI there, that middle one, and then the blue ones here is just another access point for the SPI. This is just for my convenience. When I was working on it with the logic analyzer, you can just connect your logic analyzer there. And down here we have along the edge some more pads. This is just repeating the SPI. I find that putting things on the edge of the board like that is quite a convenient way to connect stuff. And if you're going to have empty space, you might as well fill it with another connection. So all these ones along here, I've done the same thing. Each of these pads is just the same as the pin that's next to it. Just gives you another point to connect to. Up here we have 2 analog inputs and the ground and the VCC that you would need to go out to those as well. In my earlier testing, I was using those for a joystick for controlling the X and Y position of the spindle or whatever you got. I'm not sure if I'll do that in the future, but yeah, probably will. I'll come back and do that again. Here we have 4 opto-isolators, and like I say, I haven't tested these yet, but pretty sure they should be okay. And this is useful for if you have a higher voltage limit switch system, like those inductive position, or what are they, inductive limit switch sensing things. they typically run on about 24 volts or 12 volts sometimes. So if you want to use those, you would pass them through this black and yellow pin there, and they would go into the first 4 digital inputs. And the first 4 digital inputs are here as well, but this is just 3.3 volt inputs, so you can't use your 24 volts on here. This is going directly into the microcontroller. A little bit of bodge wire here because I made a mistake. I actually had to take the microcontroller off and cut a trace underneath it and put it back on, and then put these bodge wires on. A little bit of a nuisance. So yeah, we've down here we've got 16. No, sorry, this last one here is a VCC there. So we've got 15 GPIO that could be either inputs or outputs, but one of them here, this one that's marked PWM, this one has to be, if you want to use PWM for your spindle speed control, it's going to have to be that pin. So I thought I'd just mark that as PWM anyway, because that's probably what most people would end up using it for, I think. So putting that in the middle, then we've got, the default firmware I've set up to have 7 inputs and then another 7 outputs up to there, so 8 through to 14. The 8 here, D8, is also going to be on this LED, so when D8 output goes high, this LED will go on. That's mainly just as a convenience when you're setting stuff up. You might, because the only other way to check that this pin has gone high is to put an LED or something on there yourself. It's just convenient if there's one on board that you can check it quicker. Then we have a power LED, and then there's a connection LED, which this one will turn on. This is the green one that we saw before. This will turn on when the connection between the between the Raspberry Pi and this is all up and running properly. Over here we have obviously the step stick carrier thingies with the capacitor inside there, and these pins here are for the micro stepping control. If you want like 8 times micro stepping or 16 or whatever, you can set those up there. Unfortunately, I didn't realize, I designed all this a little bit hastily perhaps, because I didn't realize that these TMC 2209s that I was using, even though it says quite conspicuously on their UART, I didn't realize that you could use that UART to do all the settings for current, to set what current you want them to be running, and among other things. So I think if I was designing a revision of this in the future, which I probably will, at least to get rid of that bodge wire, I'll be doing a new revision. But in another revision, it would be nice to use that UART instead of relying on these stupid little potentiometers on here, which they're bloody useless, those things. I bought a whole bunch of these, and after having so many that didn't work, I realized it was all the fault of these little potentiometers. They're just crap. They really let down these otherwise quite nice stepper drivers. I really like the TMC 2209. They're nice and quiet. Anyway, so we've got 4 outputs for those. Up here we have the stepper outputs, and you could either use these screw terminal thingies, of which there are a whole bunch on there that just focus for me, thank you. And then on this side there's a input for the power for the stepper drivers there. So this can be up to whatever voltage the stepper drivers will handle. Is it 22 volts or something like that, I think, for those maybe? But whatever the stepper drivers you put in here, whatever their maximum voltage is whatever this maximum voltage is going to be. Yeah, so you can use these screw terminals, or you can just, if it's more convenient, you can use these pins there to go out to your steppers, which was what I was doing just before. Down here we have a 3 volt power supply or regulator. That's just to supply power for the microcontroller. Here we have 3.3 volt signals, so these are the step and directions. So we've got step dir, 4 pairs of those, and this is what I was connecting to before to control that larger external stepper driver, which does accept 3.3 volt signals. That's the only reason I could use it with that. Down here we have a level shifter. So the idea was that this 5 volt input here would be powering this level shifter, and these 3.3 volt signals could be converted to 5 volt signals for stepper drivers that need a 5 volt signal, which is most of them, I think. I just got lucky with the one that I have. I could use it with the 3.3. But this logic shifter, level shifter, just doesn't seem to work. I don't know what, I set everything up properly, so I think in future I might just delete that. It's a Texas Instruments TXB0108, and I've seen a lot of people having problems with these in forums and discussions online. So I think I'm just going to get rid of it completely, and I'll try and buy a stepper driver that can handle or that can accept the 3.3 volt signals in future. So these pins are probably going to disappear as well in the next revision. The 3 yellow pins next to there are for an RGB, like WS2812 I think is the protocol, RGB LED strips, and they run on 5 volts typically. And then next to that we have ground, VCC, data and clock, and this is intended to be used for a rotary encoder. That's what I was using it for just before. But this clock and data could also be another 2 GPIO pins if you wanted them to be. And I think I've covered just about everything there. Oh, this little bit that I've stuck on there, that's just for my for the dongle to upload the firmware onto. Oh, I should probably say something about this 5 volt input here as well. I didn't put a 5 volt regulator on here, even though we could have used the power that comes into the stepper motor drivers there, which is almost always going to be higher than 5 volts. And there is a bit of space here. It looks like I probably could have fit it on here, but I have a lot of these like BECs for my RC planes that can already handle pretty decent amount of current. Like this one can handle 7 amps. And if you're going to power the Raspberry Pi through this, you want at least 3 amps, I think, ideally. So I thought I'd just use one of these, and I've been connecting it to this terminal block. I just put it in there like that, so it can get whatever power the stepper motor drivers are getting, and then we'll have 5 volts here, and we want 5 volts here to power this regulator for the 3.3 volts for the microcontroller, and to power the RGB LED strip there, and to power the level shifter. Maybe not in future, but for the time being it's getting 5 volts there as well. And also this solder bridge here, if this solder bridge is closed, then that 5 volts will be taken straight through to this pin header here. There's a couple of pins there for 5 volts to power the Raspberry Pi. And depending on the type of Raspberry Pi you have, some of them I think it's safe to also power the Raspberry Pi via USB on the other side. So you can have this 5 volts and the USB 5 volts. Just to be on the safe side though, because some variants you can't really do that, I read. So just to be on the safe side, if I'm powering the Raspberry Pi from its USB connection, I will disconnect this one so that it's not getting both 5 volt supplies. The other reason to do that I've found is that quite often I want to fiddle around with something on the stepper drivers, or maybe even disconnect a motor completely. And with a lot of these stepper drivers, it's not safe to just pull the motor out while it's powered up. So you're going to want to turn this power off to like swap a motor over or something. And if you turn this off and you're back powering the Raspberry Pi through this, then you're going to have to turn your Raspberry Pi off as well, which is kind of slow and annoying if all you wanted to do was swap a motor. So for that reason, most of the time until now I've been using USB to power the Raspberry Pi. Also my USB is coming from my computer, which is connected to a UPS, so even when we have a power cut, my Raspberry Pi will not just suddenly get turned off. And I discovered recently that if you do that, you can corrupt the SD card, which really sucks. So for that reason, for most of my development have not been back powering it, but in the future when everything's configured the way I need it to, and I'm not going to be changing things all the time, I think then I'll put this solder bridge on permanently, and I'll just have my Raspberry Pi in here permanently powered from this. Okay, let's try that again, but this time while we're looking at the graphical user interface. So hopefully this will help to explain what was going on with these motors moving. So we're looking at the Raspberry Pi over a remote desktop, and I have opened up the LinuxCNC GUI, but I have not connected to the real-time unit yet. And this text here, this is what I was meaning by the LinuxCNC text, which is probably going to be the default thing that's open when you start this Axis GUI. So Axis, a little unfortunate this name, it's a little bit confusing, but Axis is the name of this thing, this program that we're looking at. So to get it all connected, first you need to turn off e-stop, and when I do that we'll see we get a LED here. This is actually the mode LED, and green means we're in manual mode. So this will be blue for auto and red for MDI, I think it is. And this little LED goes on here as well, so if I just turn it off and on again, we'll see that LED. And that just signifies that the SPI connection between the Raspberry Pi and the real-time unit is up and running. Next thing we'll have to do is turn on the machine. So that's this button here, when we get another LED there. So when we've got two greens here, or when we've got this green here, we're good to go. And then normally I guess the next step would be to home the machine. This is obviously not a real machine, it's just a dummy machine, so it doesn't have any limit switches. I don't think I need to home it actually to get the program to run, but I'll just home it anyway like that. And then you would run the program by either clicking play, this play button there. In my case, since I have this little dinky little control panel, I'll push my green button to run the program, and now we can see a little bit clearer probably what was going on there with those motors moving around. And you can probably guess which motor is which from the way they're moving. And then I'll just let it get to the eye, so it's over the side a little bit, and then I'm going to stop it with my red button, so I can do that. And then this yellow button in the middle that I didn't really show you before, that's going to do a touch off, and it's going to set all of the axes to be 0 at whatever the current position is. So at the moment we're at x18, y 0.49, but if I press my yellow button, this will touch off so that everything is at 0 or close to 0. It doesn't seem to quite get to 0. I'm not sure if this is because that's the resolution of the steps it has available or what, but yeah, sometimes it just goes to slightly off 0. So that is what was happening there, and I want to look now at what features in the hardware abstraction layer the real-time unit makes available. So this might be a little bit confusing for those of you who are not familiar with LinuxCNC, but we have this thing here called Show HAL Configuration, and then under here we have pins, and if we go in here we'll see something called weenie, which is what this real-time unit has been called. And I'll look at this one here called encoder first. If we look in here, there's a value called jog counts, and that's set to -5 at the moment because I was fiddling with it a little bit earlier. But if I click on the watch tab and then click on this again, so that's -5 is the current value, and this jog counts number will be incremented or decremented by moving the rotary encoder. So one click is 1, the value changes by 1 there. And as I mentioned earlier, in my current setup, the configuration I've made, I have connected this encoder jog counts to the feed override value. So if I do that again, where we're looking at the look at the feed override slider there, so we'll see I can slow the feed down by what is it, 5% per click. So that amount that it's going to change by is configurable in the settings file. Of course, it doesn't need to be 5%. And that's just what I have chosen for the time being to use this rotary encoder for. But obviously rotary encoder would also be quite useful as a manual pulse generator to jog the axes around and get things into position. So you could set it up to be, you know, whatever you like. And let's have a look at, I mentioned analog, so there's two analog inputs here, and they also each have a jog counts value for the same purpose really. You could use them for the same kind of things. This is a little bit different in that, for example, if you use this as a joystick, you would hold the joystick over to one side, and this jog counts value would go up all by itself. Depending on how far away from center your joystick was, it would go faster or slower. So you could use that to jog axes around as well. And then there's this one called buttons. There's another jog count, so there's actually 4 ways to do jogging. This one lets you designate 2 digital inputs on here to be 2 buttons, one of which will increment this jog counts value when you hold it down, and the other one will decrement that value. And which axis that will jog, or what feature it will change, again, will just be configurable in the LinuxCNC settings. All very configurable, this thing. Then we have, under input, we have 16 digital inputs. The first 3 of those I was using as my red, green and yellow buttons there. And then we have 16 outputs, which I'm not using for anything in this current little setup. And then we have RGB. So we have 16 RGB LEDs, so that's for this RGB LED strip here. And in each of those we can toggle the red, green and blue components individually. You can't set a smoothly variable color like a floating point number. You can only turn the red on or the green on or whatever. So if you turn, say, red and green on, that will give you yellow. So if you think about that, you get 7, well, it's 8 possibilities, but one will be that the LED is off, right? So you basically, it's either off or you've got 7 colors to choose from. And then the last thing we have down here is spindle, and I think most LinuxCNC users, at least if you're using LinuxCNC for machining, will be familiar with this. That just lets you use that PWM output that we had there to set the speed of your spindle. But keep in mind that these outputs are only 3.3 volts though, and I think a lot of spindle controllers, they require a PWM signal that goes between 0 and 10 volts. I think that's pretty common. So if you wanted to use that, use this for those, you'd need to have a transistor and a 10 volt power supply somewhere out external to this to use that. Now, for those who are not familiar with LinuxCNC, you may be wondering, how are these things all connected? Like, how does this system know that this button should do such and such a function in the software? It's basically all set up in these text files, and I'll just give you a quick look at one of them here. In fact, I'll just look at this one here because it can be a little bit intimidating at first to figure out what's going on. But these 3 lines that I've highlighted are how I've set up these 3 buttons to be used. So remember, we had weenie input 0, 1 and 2, or 0, 1 and 2, I'm not sure what order. So that's what these 3 lines are here. We're basically just saying that weenie input 0 is going to call this feature inside LinuxCNC, so program stop. Weenie input 2 is going to be program run, and then this one in the middle, this is my yellow button. The yellow button is going to do MDI command 1, and it's a little bit kludgy sometimes the way LinuxCNC works, but what this is doing is referring to a second settings file, this other file here, and you can set up a whole bunch of MDI commands here. MDI command just means like a little piece of G code that you can call whenever you like. You don't need to load in a program to run it. You can just run one line of G code on demand, basically. So MDI command, this first one is MDI command 0, and this one is MDI command 1. So this little piece of G code there can be whatever you like. That's going to be executed when I push my yellow button. So LinuxCNC is very, very cool. I like it. It's lets you configure things to a crazy degree. I like it. So that's basically what I wanted to cover in this video, but I do want to also show you one other thing that I've been working on that's quite cool. You may have wondered at the beginning of this video, how was I able to set up that program to run without having any keyboard or monitor or mouse or anything connected to the Raspberry Pi to set it up. And that was done with this thing here. It's called LinuxCNC G-Code Server. So this is a server that will run on the same computer as the LinuxCNC is running on, and it will open up a network connection, and it will listen for basically G-code commands, although there's a few other sort of specialist commands that we have there as well, because this was originally, well, one of the reasons it was made was to allow OpenPMP to connect to LinuxCNC and issue G-code commands to control it for a pick-and-place machine. You see where this is going? So that's that's one of the reasons this exists, and I'll just show you a little bit of how it's done. Another reason I wanted to have this is so that we could completely do away with this LinuxCNC GUI. So LinuxCNC allows you to start it up and not have any GUI at all. So this whole window that we're looking at there, it just never opens up. And so that's what I have done. And instead, well, I haven't done it this time, but I'm leaving this open so you can visually see what's happening over there. But we just open a telnet connection, so like that, and then we can issue some commands. I'll just check status. Okay, so the machine is on. We're in manual mode. all axes are homed and the position is that, and we can check what file it has open, and we can say open we can open another file to run like that, and then we can say run. We can do home, enable, all those other things, but it's already homed and enabled, so we'll just do run, and then that will run the program. We can do stop, nope, we can do abort. If I do abort, it will stop like that. Let me just reload that so that it's in the right place. There we go. Yeah, one thing about using multiple ways to interact with LinuxCNC is that they don't know what the other one's doing. So this graphical user interface here doesn't know about anything that my buttons are doing over here or what the server's doing. So it didn't know that it needed to update this view after I shifted the home position before, when I did that touch off to zeros. Yeah, so that is how I was able to run the program at the beginning, and yeah, that's it. So I might actually come back at some point in the future and make a proper explanation video of how this works as well. It's still in flux at the moment. There's a few things might still change, not much really. It's in a pretty good state, I think. But anyway, that's how that was working. So that's the end of this video. Thank you very much for watching. See you next time.